Welcome to Real Physics. This is about the Machian Gravity Meeting recently held in Bonn with Dennis Braun, Jonathan Fay, Jan Preuss and myself. The talks and discussions are a little bit more technical than usual, thus if you're interested in the details I encourage you to look up my variable speed of light playlist or the papers linked in this video. Enjoy watching. Yeah, we are talking about how to calculate gravitational constant, and I would like to have a concrete formula. I mean, we have the order of magnitude coincidence, G equals c squared radius of the universe and mass of the universe, and this of course, this is approximate and also of course approximate. There would be a factor in between, c squared divided by sum over m over ri. So, but the question is there a factor, is there no factor? Sciama needs no factor, but I'm referring to the paper by Dicke, and Dicke in his equation 5 in 1957 paper, he says that the index of refraction is 1 plus 2 gm over r c squared, and this is justified by the test of general relativity. There is no doubt about the correctness, and I mean this is correct not only orders of magnitude, but the factor is correct here. But usually when we consider the gravitational potential, we're talking about c squared rather than c. And what I'm referring here to the difference, that means if this is larger than 1, so the velocity outside the gravitational field would be c, and this would be the velocity of light in the gravitational field. But I'm considering the square, c squared over c not squared, and obviously if you square this, so you get here a 4 in first approximation, because this is small, so you have something like this in first approximation, 4 gm over r c squared. And then if you take this idea saying that, oh, this one might arise from the rest of the universe, this is just a little contribution 10 to the minus 6 from the sun, this must be a sum, the respective sum over all masses in the universe. But of course, you have to sum up all masses in the same manner. So you would get, this sum here. Sum over ma over ri is, at the end you would get this factor. G would be c squared, not just, but a factor 4 here, okay? If you do the summation correctly. So we have a problem here. And I found that pretty convincing, but at the same time I wanted to check and test it. And I mean, if you consider a gravitating body, say, let it be the Earth or the Sun, here inside the gravitational field, and here you're outside with your regular C, and if you neglect the evolution of everything of variable scales, forget about the cosmological evolution, time derivative is 0, so you can compare the energy. Obviously the conservation of energy if a free-falling body towards the gravitating body. So what you want to have conserved is E equals mc squared. And if you apply the product rule, that would be, if you look at the change, that would be a d change of mass c squared plus the mass and the change in c squared. Yeah, I should add that the problem that arises here, that usually you say the gravitational potential is gm over r, of course the sum, and here we have a factor of 1/4. So what to do with the factor here? But if you consider this situation, then and you realize that everything has variable scales, you have different scales in here and out there, And it turns out that C is slower here by 2 factor units. I mean, one arrow would refer to just 1 gm over rc squared, just 2 arrows would be slower, and you have the frequency is just 1 arrow lower, and the wavelength is just 1 arrow lower. But changing the frequencies and the length scales, you affect also velocities and you affect accelerations. So you see that all accelerations would be diminished here, are slower. And of course, if every acceleration is smaller, then you have the apparent inertial mass being higher here in a region with lower speed of light. So this change of the mass accounts for 3. This goes up 3 times, and this the change of c squared, of course, goes up 4 times, and the remaining, just the remaining 1/4 of this potential energy is translated into kinetic energy, and that's why you're fine with the potential 1/4 of c squared. This could take the role of the potential, because I mean theoretically the potential would be c squared, but 3/4 of it go into the mass, you know. And I always thought that okay, this is fine, this is consistent with Dicke's idea and this hypothesis on c squared. But I also that fits nicely, and I convinced myself of the factor 4 here. But maybe you have objections, or tell me where do you see the wrong or arbitrary assumption here?
I have a heuristic arguments for the Sciama's expression.
Yeah. I mean, of course. I mean, if you look from another side, you are right at variance. But I mean, where's the wrong thing here?
Well, it's a bit difficult to follow with all of the changes of scale of the different units.
Yeah.
So
I should clarify maybe. These 2 would mean 2.
2 times that.
2 times, and this would be 4
Yeah,
times,
and
one arrow just refers to a factor 1 plus gm over rc squared. We're talking only about first
right, so that's why
approximations.
factor 4.
Yeah.
Okay. Well, I mean that it makes some sense, although I'm not sure the 1/4 c squared at the end, how that fits into.
No, you said, okay, I want to move a particle from here to there, but then I want the energy to be conserved, so c squared is just the potential, okay? The total energy.
But shouldn't the particle gain momentum when it moves from here to here, so you should have the relativistic...
Well, I just would say that it gains kinetic energy.
Okay. But how is that accounted for in the equation?
So mc squared is just supposed to be the potential energy of the particle, right? And
the total energy, mc squared, is the total energy.
But you need the potential. You need the motion term, like the pc squared, right? P squared
yes,
c squared.
you can do this. Just.
That there are hidden assumptions all over the place, and that's what I'm asking. Why I'm asking why? Because I mean, potentially it could be wrong. So I mean, we need to eliminate the wrong assumption.
Let's take a picture of the board, because then I'll wipe off the bottom half and then compare like some of this reasoning to total by Sciama to wipe anything. So.
Maybe we should put that back to 2.
I can just turn it to squared. And just take away the pen, maybe.
Okay, that if you put the square, there would be a 4 here. Square 4 in first approximation. Okay.
So Sciama's expression, I think, has a sort of strong heuristic case for it, based on an extremely simple argument, right? And it's also worth pointing out. it's also worth pointing out that both Schroeder and Schrödinger have a 2 here, right?
It depends. It really depends on the factor that you put in front of the kinetic energy.
Okay.
So if you set it to 1, which is of course the most natural choice, then you get a 2. But if you
set it to
choose an arbitrary k, then you get something like 2k in the denominator.
Alright, that's interesting. But, okay, so Sciama's expression is like this. Now the reason why I just like this one is... Wait, no, this is not correct. Sorry.
It's the other way around.
Yeah, it's the other way around. Okay. Is if you simply rearrange this, we have c squared equals g. And then you put your test mass in front of this. This is the energy, the energy of your particle, the mass energy, and this is the gravitational potential. You know, this is negative. So GPE of the particle with respect to all of the other particles in the universe, right? And so there's a perfect balance of the particle's rest mass with its gravitational potential with respect to the rest of the universe, right? And I think you can even find another correspondence if we take the vector part, the vector correspondent of this equation, of this expression, where you would have like the momentum of the rest of the universe being compensated by the vector potential generated by the rest of the universe on your particle. Your particle's momentum with respect to the rest of the universe would be compensated by that vector, right? And so there's a balance, I think, both in the scalar and the vector parts. And what it suggests is that every single particle in the universe has a total, you know, this is negative, and this is positive. So the total energy of any particle is going to be 0, right? And the reason why I particularly like this is sort of related to this cosmological thinking. If we take energy conservation as a kind of rational principle, a regulative principle rather than this empirical fact in subsystems, we take it as like a principle that has to apply by definition the cosmological scale, then the only sorts of laws of physics that would allow you to get to be truly universal, which means that they can withstand, you know, essentially the creation of the cosmos, would need to correspond to laws in which the energy is in total is 0, right? And so the idea is that if your energy of any given particle is 0, then getting new particles coming into your cosmos is not a problem that your law can't deal with, right? It's not a problem that stands outside your law. And so that suggests that your law is then capable of being truly universal, right? If that's the kind of reason it makes it.
Would that imply energy conservation over time?
It would imply that you have perfect energy conservation over cosmological evolution, right?
Yeah, but I don't know if I want that.
But you're thinking of energy in a different way, because...
Yeah, I guess energy was invented because we sought tiny independent laws of energy.
But that's an inherent part of what we're trying to do, right? Because we're trying to find the most universal laws, and if we sought time-dependent laws of nature, we would be giving up on figuring out how those laws evolve, right? And so
there is an important
we'd be stopping halfway.
I know, I agree, of course, but I mean, it could well be that the time evolution of the cosmos and the time evolution of energy was overlooked, and it's just not our conventional definition of energy does not match, does not include this evolution. And of course we have to arrive at a new law which also encompasses the
But
evolution.
then you would also have arrived at a new
Not
energy.
necessarily it's the same definition of energy, right? So, yeah.
Okay, but yes, but then you would arrive at a new concept of energy. But I have this kind of debate with a friend of mine quite often, where he's sort of suggesting that maybe the laws of physics generally evolve creatively like an organism or something, and that,
Okay, yeah.
and that there's some kind of law. Yeah, but I don't, my intuition is more that the laws of physics, if they're evolve according to laws, and therefore there should be meta laws that govern those, and that we can push this process back and find a truly universal.
I agree so far. Just I mean, if it's the same thing, you're basically using the same thing and postulating that.
But I'll also mention. So Dennis Sciama points out this fact in his paper of 1953, and it also stays with him. So by the time he makes his interview in 1978, he's also realized that this relation might correspond to the flatness condition, the critical density condition for flatness of the cosmos at large scales. And there's a quote by Sciama in this interview, I think it's on the API website, where he says something like, he still has a secret hope that the Machian way of thinking about things, according to the Machian way of thinking about things, gravity is, would perfectly cancel out the energy, the mass energy of the particles, and that this would give him a condition for the Einstein-de Sitter model, which is the flat cosmos model. Right.
Yeah.
So Dennis Sciama was still thinking along these lines, or hoping that this would work out, right? Even in the 70s. So, I mean, this is the sort of vague heuristic that makes me like this particular expression.
As an idea, it sounds beautiful. I don't deny that. It's just that we still have to wonder about that. There is, to make the confusion complete, maybe. You're arguing for factor 1, and I argued for factor 4. But if I'm not mistaken, it is Schrödinger who has a factor 2.
Yeah, exactly.
There.
He has a 2.
Does anyone remember how this justification in the 1925?
I think he's getting it. So
it comes out the same way as the factor of 2 comes out in Schrader theory, because he just uses the Weber potential, and then you get the same factor of 2 in that.
Yes, because if you do the integration over the universe, the factor 2 changes into 3, right? That's, if you're referring to R.
No. If you have to, if you want to get the correct perihelion shift, you have to put a factor of 3.5 in front of it, and then you gain a factor of 3.5 times 2, and this is the same way that Schrader also gets. He has to.
So he fits into the perihelion shift.
Yes,
That's exactly what Schrödinger does, right?
Yes, exactly. This is why they're getting the same factor. Because Schrader also gets, when he sets the k equals to 3.5, then he also gets.
But this is an a posteriori result, right? Fitting it to the perihelion shift.
Yes,
they're not deriving it from.
This is why I'm not arguing for it. I just set it to 1. I would not.
Factors don't matter. By the way, Dicke fitted it to the light deflection and the Shapiro pendulation.
It's
too much a posteriori.
It is a classical theory anyway, so it is astonishing that it even yields a perihelion shift on one. But it is just 2/3 of the value.
So I'll just comment also on this, right? Because we have the same expression that we can read in different ways, right? And it appears in the G naught of like Schwarzschild metric. You have like 1 minus 2 GM over RC squared.
Yeah, the minus we all just like.
Yeah. But then if we interpret this as 1 plus GM over RC squared, and sort of allow for approximate reasoning here, then we put -2
Mm-hmm.
power, then this can just become your potential of the universe, right? This is the sum of all the masses. That's -2.
That's what you're. Okay, so basically, I guess, I mean, what I did propose is like squaring this, and you proposing taking the square root. That's why you are
Yeah,
factor
yeah.
of 4. Yeah.
One arguing for the third power.
And but to me this is neat, just because I use this for my scale invariance requirement, and deriving gravity and so on. So yeah, so that works in my model. But yeah, the danger is that we deviate from the perihelion shift.
Yeah.
Yeah, but frankly, this is not only your problem; it's also my problem. I mean, it's not that the other thing. So
So we need to like calculate that in detail again and see.